All right. Hello, everyone. Welcome back. Math 154, week 4, lecture 2, our 8th meeting together. Per usual, whiteboard on the screen. Just going to take a few minutes to cover that, as well as one or two other details, or due dates, and then a couple other details, that is to say. So my math lab homework 2.3, due today. No surprises. 2.4, due the 22nd. Also no surprises. Then we've got 3.1 and 3.2, which will both be knocked out today. 3.2 is a relatively short section, so those will be due in a week on the 24th. For Excel, we've got the 1.8 BMI due today. Then we've got the currency file due in 5 days on the 22nd. Fair warning, the next one is going to be 2.4 CPI. I'm probably going to do a super quick memo about that one at the start of next class, just to clear one or two things up, but I'm not even assigning it yet, so I don't want to mention that yet. It would be confusing. We got several discussion boards, one due today, one due the next class, and then one due a week from today. We will obviously talk about the week 4 lecture 2 discussion board during class today. This is going to be another one of those where not everyone will necessarily have a chance to participate. So if you've had one or two that you've missed already, you absolutely positively need to make sure that you get that one. And like I said, there will be several more discussion boards where everybody has a chance. But unfortunately, using those guided activities to as a catalyst for the discussion boards is how I was trying to phrase that. Most of those have very limited opportunities. You do have a quiz that's going to be due on the 22nd from the guided activities. I believe I said that's probably going to be the only quiz from the guided activities. It's just a quick 2-question quiz. We talked about it last time, so if this is news to you, make sure you're watching all lectures completely. And there will be a quiz assigned next time, and there is likely to be a quiz assigned the time after that as well. I want to go ahead and knock a couple more quizzes out, since we're getting close to chapter 4, which means getting close to the midterm, and I don't want to have a bunch of quizzes kind of right around the midterm. I don't want to have 2-3 quizzes due back to back when the midterm's going on. Same with Excel assignments. We'll kind of take a breather for a week on those, most likely. And then just a reminder, I mentioned this last class, but I do have something going on Thursday, the 24th. I will not be able to host class live. However, you will still get a full day's worth of material, whiteboard, lecture, new sections, assignments, all that stuff. It's just I will have to have everything recorded ahead of time, and I'll put it straight up on YouTube, and the link will of course be in Canvas like it always is. It's just instead of it being available after class, it will be available before. I will make sure it's available all day, the day of class, the 24th. But if I have everything, finished on Wednesday, I'll go ahead and have it posted. So maybe you'll happen to catch it a little early if you wanted to watch it early. So I would, per usual, appreciate it if you can watch it during the class time on the 24th. However, just like per usual, if you do not have that opportunity, you can catch the replay on YouTube whenever it is convenient for you, as long as it's before the next class. But when we come back on, what's that, the 29th, everything will be back to normal. All right, so with that being said, we're going to pick up where we left off in 3.1, talking about dimensional analysis, something that's very, very useful, something that a lot of people discard or don't try and learn enough to understand how actually simple it is and how many branches of mathematics it can actually kind of get your foot into the door of, whether it be super simple stuff or extremely complicated stuff. But let's not waste any more time. Let's go ahead and get back into that.
So let's get back to where we left off. So last time, and you had some things handwritten on the screen that weren't saved. That's okay. Just go back to last time's video, and it was just me literally doing the same example that is typed on the screen. I also did it a wrong way and told you that if you're actually paying attention and seeing if things make sense, if you're using your units, if you're keeping the words there the whole time and canceling them appropriately, if you had multiplied by 1 mile over 5280 feet, you got units that were feet squared over miles, which would be feet squared per mile. Don't even know what that unit is. The number in the answer wouldn't have made sense. So that's a simple problem that we could be able to say, all right, well, 0.75 miles is definitely not 0.000 like 14 miles square per foot. The number didn't make sense. The units made no sense. So we had a sad face for that. So again, the main idea with dimensional analysis is out with the old, in with the new. Again, out with the old, in with the new. You are trying to cancel your old units, your feet, your miles in the instance of this example on the screen, and then you want to be left with the new units. But first of all, it's not always just one conversion factor. It's not always just one multiplication of a fraction. Sometimes you'll need 2 or 3 or 4, as we'll see today. Or if you were going to instead do it as a proportion, then you'd be solving 2 or 3 or 4 proportions, which gets a lot muddier and leaves a lot more room for mistakes. Now, I've already said I don't care which way you do things ever in this course, as long as you have a way that you can do it that works 100% of the time. So if you want to do everything with dimensional analysis, with this multiplying by a fraction, you do it that way. If you want to just keep doing proportions over and over, you can do it that way. You will see me emphasize the dimensional analysis since we've already done a whole boatload of proportions together. So I'm going to leave that method to the side. I introduced it at least once for this section, so you have your idea. But here's the thing. The types of units we're going to convert aren't always just units. Sometimes they're what we call rates, something like miles per hour, or feet squared per mile, or miles squared per feet, or whatever. That would be a garbage one, but it's still a rate. It's where you have a unit on the top and a unit on the bottom. Once again, like miles per hour, or students per teacher, or I don't know, light bulbs per closet, apples per orange. So what exactly do we do if the old units were originally in the bottom? What if we're dealing with one of these rates? Maybe we start out with something in miles per hour and we want to convert it to miles per minute. Why would we ever want to do something like that? Why would we want to convert miles per hour to miles per minute? Well, let's say you're on the road and your phone dies, your GPS dies, whatever, or you just have no signal and everything just goes kaput. And you know you have a turn in 5 miles and you know that you're going 60 miles an hour. And you go, all right, well, how much time is going to pass before I need to take this turn at 60 miles per hour? Well, you know it's 5 miles from now, so you could convert your speed in 60 miles per hour to miles per minute, and you would end up getting 1 mile per minute. I'm going to save you the work. And then you know, all right, well, if I'm going 1 mile per minute and the turn is 5 miles down the road, I need to take my turn in 5 minutes, because 1 mile per 1 minute. So that would be very, very helpful, and that is a trick that I have absolutely used in my life. More before the cell phone age, because I usually have a full charge, full battery, and just go ahead and have the GPS set up ahead of time, but you get the point. Sometimes things go wrong. So in that instance, that example I just quickly discussed, what if the old units were originally in the bottom? Where would you put them in the multiplier to get rid of them? So that example that I just verbally discussed, we're now going to show it. So, and wink to someone that just said something. Got my right pen, there we go, example. So we're going to convert 60 miles per hour, which is the same thing as writing that as 60 miles on top of hours. I'm just saying that's the same thing. 60 MPH is miles on top of hours. And we're going to convert this to miles per minute. Remember, the abbreviation for miles is MI. And I know it seems goofy, I guess, that MPH is MPH, miles per hour. But traditionally, M stands for meters. Again, traditionally, M stands for meters, not miles, unless you were using the abbreviation MPH. All right, so what's the idea behind this? First, we're going to write the original number with its units. So we're going to first write the 60 miles per hour with their units. Now we got to write it this way. We're not going to write it as MPH. We got to write the miles on top and the hours on the bottom. Now, if you wanted to do it like this, that's fine as well, because the 60 goes in the top. There we go, miles, hours. And we want the hours to convert to minutes. So the hours are the old that we've got to be out with. The minutes are the new that we want to be in with. So we multiply by a fraction in such a way that the hours will go away and we'll be left with minutes wherever the hours were before originally. These hours are in the bottom originally, and the whole idea is that you want to put your units that you want to go away in the opposite position. So since these hours are in the bottom, in this multiplier, they have to go on the top. See, remember I said I figure out where my units go before even thinking about any numbers. That way these will cancel and we'll be left with whatever unit I decide to put in the bottom, which we're going to go with, of course, minutes. So now we just got to ask ourselves, well, how many hours is how many minutes? Hopefully everyone knows that 1 hour is 60 minutes. And again, we'll see our hours cancel. And the miles are still left in the top. They don't cancel anything. The minutes are still left in the bottom. So this is now in miles per minute. And then you have a 60 in the top, a 60 in the bottom. They cancel exactly. 60 divided by 60 is 1. So you get 1 mile per minute. You could write it that way as a fraction, or you can write 1 mile per minute. I'm going to remind you for the, I don't know, 10th time, 5th time, something like that. The word per means the next unit goes in the bottom. The word per will always mean that the next unit goes in the bottom. So if you need to type that up, the word per means the next unit goes in the bottom. That is extremely important moving forward. So again, our 60 mile an hour drive is equivalent to a 1 mile per minute drive. So we know if we got to go 5 miles down the road, it's going to take 5 minutes with that very simple number. Now you might say, well, what if I was going 75 miles per hour? What would that be? You would end up getting 1.25 miles per minute. And then you'd have to do a little more math. You'd have to take 5 and divide it by 1.25. And we'll explain how we would have known to have done that later in this chapter, in fact, just by trying to get an answer with appropriate units. It's this idea of unit math, not even just dimensional analysis. There's a whole field of mathematics, and a lot of people like to call it math on the back of a napkin. Because you just try and break things down as simple as possible via multiplying, dividing, adding, and subtracting, and just making sure the units in the answer are correct. And then you say, well, if my units are correct, the number's probably correct. It sounds like a load of nonsense, but it is fascinatingly accurate. All right, so this is going to be coming up every now and then. So don't just think it's always going to be canceling units in the top originally. Sometimes the units you need to cancel are going to be in the bottom. All right, so what if we have multiple versions? And I don't need this in bold anymore. Let's take that off. What if we need multiple conversions? For example, what if I asked you to convert 2 years to minutes? So you could say, well, first of all, how many minutes are in a year? And someone might know that random factoid off the top of their head. Someone into musicals might know how many seconds are in a year, or whatever it is. Maybe it's minutes, maybe it's seconds, doesn't matter. We don't have to know that. We don't need to know it's 5,722 minutes and that number was completely made up. It's a much larger number than that. We just need to be able to go in incremental steps. So we're starting out with 2 years. So the first thing we want to write is 2 years. And that years counts as in the top because it wasn't 2 per year. If it said 2 per year, the years would be in the bottom. And then we multiply by a fraction, and we want to get rid of the years. We know we want to get rid of the years, so that goes in the bottom. No matter what I convert to, I absolutely have to get rid of years. They start in the top, so the multiplier goes in the bottom. Now we got to think in simple ways. How can we go from years to a smaller unit of time? You might say we'll go to months, and there's 12 months to a year, and that seems okay at first, but if you remember a week ago, I said we don't know how many days are in a month because it varies from month to month. We don't want to just say 30 because only half the months are even 30. Some of them are 28 or 29, some are 31. So it's a bad idea to go between years and months, but we do know exactly how many days, and we said we ignore leap year. Sorry, leap year babies. If you were born on February 29th, we are ignoring your birthday, and you were born on either February 28th or March 1st, just for simplicity. So we say no matter what, 365 days in a year. So 365 days in a year. So that's 1 year is 365 days. So the years are gone, and now our units are days. And you could write equals and do the math of 2 times 365, but I'm not going to, because we're supposed to be converting to minutes, and these days are not minutes. So we're a little closer to minutes, but we're not quite there. So now I'm going to do the same thing again. I need to multiply by a fraction where I'm converting from days to something closer to minutes. Well, I don't know how many minutes are in a day off the top of my head. That's a lie, I actually do, but I don't expect most people to. Most people should know, and in fact, every single one of you should know how many hours are in a day, though. There's 24 hours in a day. Well, which one goes in the top? Which one goes? I'm just going to assume to put the 24 hours in the bottom and the 1 day in the top, and you're rushing and you're doing things wrong. Don't do that. Pay attention. Out with the old. Oops, too far. The days are in the top, so in our multiplier, they must go in the bottom. So it's 1 day to 24 hours. That idea is so insanely simple, but people stall out on it constantly. And I'm speaking as not just as the president of this club, as a fan or as a member as well, because when I learned dimensional analysis, I stalled out too, just like y'all. And it's okay, because we do things wrong to learn how to do them right. All right, so now our days are gone. Now we're in hours. I actually meant to make that a blue cross out, but that's okay. Not the end of the world. Now we're in hours. Well, how many minutes to how many hours? Well, it's 60 minutes to an hour. So that's all we got to do. But where's the 60 minutes go? Where's the 1 hour go? Don't think about that. You're thinking too far ahead. Out with the old. Hours got to go bye-bye. They're in the top. So in the multiplier, they go in the bottom. And it's hours to minutes. We do know that 1 hour is 60 minutes. I said that I do not expect you to memorize a lot of these unit conversions. I don't need you to know. I'll even give you the 12 inches is a foot. For the love of being an American, you should know that 12 inches is a foot. But I would give that to you on a test. I would give you how many fluid ounces to a gallon, and how many liters to a gallon, or how many, I don't know, centimeters to an inch or miles to a kilometer. If you needed any of those, I would give them to you for the test. In your homework, you can pull it up in the view an example, or you can just go to the internet. All right, so hours are gone. So what are we doing here? We're taking the 2, and we're multiplying it by the 365 because it's in the top. Then we're going to multiply by the 24 because it's in the top. And we're going to multiply by the 60 because it's in the top. So we pull out a calculator. Ignore all that trigonometry. That's not for us. 2 times 365 times 24 times 60. Now, before I hit enter, you should be asking yourself, what type of answer do you anticipate? Do you anticipate a big answer or a small one? Well, going from years to minutes, there's a whole boatload of minutes in a year, and we got 2 years. So this better be a big answer, and it is. So if someone had divided all of those numbers, if they did 2 divided by, this is wrong, divided by 365, divided by 24, divided by 60, if they had done this, again, this is wrong, they get 3.8 e negative 6, which means it's 0.000038, which is a teeny number, and that is absolute garbage. It is not less than 1 minute is 2 years. And yes, we do get the 1051200. I'm going to put commas in here to make this prettier. 1, 051, 200. Well, what are the units? The one that we haven't canceled, these are minutes. So 1,051,200 minutes is equivalent to 2 years. Which reminds me, this was another issue that students were emailing about, the quiz. I forgot how tedious it is to set up those quizzes. So like if this was the number, I have to put out, like, I have to type 7 or 8 different variations for the answers. Like if a student put these commas, if my answer didn't account for that, it marked it wrong like it did for many of you. I have gone back and given you full credit for those if you had the commas, or if you put the dollar symbol in there, I wasn't looking for you to type that, but if you did, again, I gave you full credit. If you had an error, if you had rounding errors, that did not get you full credit. I was actually pretty nice with partial credit. You may disagree with me, but I had originally said I wasn't even going to be nice at all with partial credit on that quiz because you've got to know your rounding. So several of you need to work on your rounding. Some of you, again, will have gotten full credit. If you think I missed you, you can email me again, but I'm fairly certain that I hit everyone that turned in that quiz. And as a reminder, please turn in your quizzes. Please do your quizzes. It is only going to hurt your grade. And you can literally just go in and put that 0 for that quiz grade and just watch your grade drop, and we don't want that. Okay, so this is the dimensional analysis version. If you had done this the proportional way, which again, I'm not going to show completely, I'll show you how you would start it. You would have to first go from years to days. So you write years over days. So you're using your words, and then you go, all right, well, we know that 1 year is 365 days. So that's the left side of the proportion. And on the right side, we have 2 years, and we don't know how many days. Then you would cross multiply, and you'd get Not going to show all the work. You'd get 730, right? Yeah, 730. We get x equals 730. And because the x was in the bottom, that makes it days. And then what you have to do is you'd make another proportion going from days. That's really weird. I am under that. Okay, so then you'd make another proportion going from days to hours. All right, well, we know that 1 day is 24 hours. We know we have 730 days originally. So the 1 goes in the top because days, the 24 in the bottom because hours, the 730 top days. And then we're converting that to hours, and you cross multiply and you would solve, and you would get 24 times 730, which is 1750, or 17,520. And then x was in the bottom, which was hours. And then you just keep going. You would have to do that one more time. So again, if you think this is simpler, then do it that way. If you think the first way I did it is simpler, then do it that way, because I don't care. But I personally believe that the dimensional analysis method is better for this stuff. I think it's more efficient. And I think especially when you're doing rates, that it's easier. I find people make more mistakes with rates when they try and do them as proportions. And there's various reasons of that. They're more complicated. All right. So next thing, what if we're here now, a unit is squared or cubed? So what if you need to convert from feet squared to inches squared, or from cubic feet to cubic inches, something like that? Because if we're talking about, say, the perimeter of a room or the volume of a box or a sphere or something like that, then your units are not just in feet or inches or whatever. They're in square feet if we're talking about a perimeter, or in cubic feet if we're talking about a volume. So having a feet squared, if you just multiply by that conversion factor one time, you're only going to get rid of one of the feet because you have 2 of them. It's being squared. So the basic idea is you just multiply the conversion factor that many times. The alternative method works as well. Admittedly, I think it's kind of a bad idea to do things that way in QR, but I'll still show you because I believe in alternate methods and I don't want to dumb things down, or water things down would be a better word there. Not my favorite word. Sorry, I got distracted for a second. Okay, so you have to multiply the conversion factor that many times. So let's do an example. If you started out with, let's convert 1 square foot to cubic inches. I don't know why I said cubic there. I was looking at the word cube there. Square inches. You can't convert a square unit to a cube unit. That's impossible. You can convert square units to square units and cube units to cube units, but nothing in between. So here's what we do. I'm going to stick with dimensional analysis from here on out. So we write the 1 feet squared. So we're going to multiply by a fraction. Out with the old, in with the new. We're trying to get rid of the feets, and we want to get into the inches. The feet were in the top originally, so in our multiplier, they go in the bottom. So that was a feet squared. So I'm going to do this, I'm not going to say wrong, but incomplete temporarily. So I'm going to do feet in the bottom. All right, well, how many feet, how many inches? It's 1 foot to 12 inches. Again, you really should know that. Everyone's got a ruler somewhere around them. Okay, so what happens in this? Feet squared does not cancel feet. Again, feet squared does not completely cancel feet because there's 2 of these feet here. It's kind of like having an x times an x and then an x in the bottom. You're only able to cancel 1 pair of them. So the feet squared becomes a feet to the first, and this feet in the bottom is gone. So if you stopped, I'm going to erase this in a second because this is wrong. You'd have the 1 times the 12, which is 12, but you still have a feet and you still have these inches. So that's 12 foot inches. Question mark, question mark, question mark. This is my brain exploding. That's wrong. Foot inch makes no sense. So not an equal sign, we need to do another multiplier. We have to multiply the conversion factor that many times. So because that was a square, we have to do it 2 times. So let's multiply by the 1 foot and 12 inches again in the exact same placement because these feet are still on the top, these feet are in the bottom. So now those are going to completely cancel. And now we have 1 times 12, which is 144. Then we have inches times inches, which is, I hope you guessed it, inches squared, and that would be the answer. So this is my preferred way of doing things. And what this problem really emphasizes is, okay, 1 foot is 12 inches. And that's what you get used to. So a lot of people will say that 1 square foot is 12 square inches, and that is significantly wrong. And someone might say, well, 1 cubic foot is 12 cubic inches. And that is horribly wrong. It's actually, what's 144 times 12? 1728. 1 cubic foot is 1,728 cubic inches. It sounds a lot bigger. And the idea is, if you made up all these little blocks that were 1 inch by 1 inch by 1 inch, it would take 1,728 of those 1 by 1 by 1 cubic blocks to fill up a 1 by 1 by 1 cubic foot. It takes a lot more because of the 3 dimensions. There's more space to fill up. All right, so the alternative method is you can square or cube, whichever is relevant to the problem. It might have sounded like I said irrelevant. I should have said relevant. I was just speaking too quickly. Alternatively, you just take the conversion factor and square or cube both sides, in this instance, squaring both sides. So this is the original conversion factor, but not written as a fraction. 1 foot is 12 inches. So you square both sides, which is a rule of algebra. Whatever you do to one side, you can do as long as you do to the other. But notice how I have to wrap them in parentheses because you're not just squaring the number, you're squaring the units. So when you do that, the 1 squared is 1, the feet squared is feet squared, the 12 squared is 144, the inches squared is inches squared. So that tells us that 1 square foot is equivalent to 144 square inches. So then I could go back to the previous example and say, all right, we had our original 1 square foot. We're going to multiply by. Now we'll use this as our multiplier. The feet squared are the old. So in the bottom goes the feet squared, which had 1. And the top is our 144 square inches. You will get the exact same cancellation, the exact same answer. It's just a more compact problem. Instead of doing 2 fraction multipliers, you're doing 1. So some students are going to like the top one because of the simplicity in numbers. Some students are going to like the bottom one because it's 1 fraction instead of 2. If you're going to go with the bottom way, though, you've got to make sure you understand this side of things, because if you multiplied by 12 square inches over 1 square foot, that is an inaccurate conversion and will give you the wrong answer, as you can clearly see. Right. This C view an example for unit conversions in my math lab. What I'm talking about here, I've already referenced. When you're doing your homework problems, if they ask you to go from miles to kilometers, they'll be, if you hit the view an example, they will give you those unit conversions there. Also, Google is very helpful, although Google often will, if you're supposed to do the 3 or 4 fraction multipliers or proportions, Google will usually just give you a 1-to-1, which is not going to help you on the test when you don't have access to all that stuff and you're not supposed to have access to that stuff. So yeah, in the real world, it's awesome. Google is amazing because it just saves you the work. And I won't even be mad at you when you use that in the real world 2 years after this course is done. However, it is an awesome skill to understand with this dimensional analysis. You never know when you might just get a deeper understanding of something else because of that. Especially if someone tells you something and you're like, they did some conversions and I don't trust their conversions. Maybe I should do it on my own. Maybe I should fact check this and see what's up. All right. So again, your text also has a lot of those conversions as well. Next up, temperature conversions. Actually, we don't want to do that yet. I want to save that for later. I don't want to get too far ahead. We're going to our guided activities. Some definitions, unit of observation, unit of measurement. This isn't anything too crazy. These are just the units that pertain to your quality or category. A unit of observation could even be something as simple as nationality. A unit of measurement is generally something that's mathematical, feet, centimeters, miles, years. Conversion is the process of going from one to the other. Conversion factor is the fraction multiplier that we were doing with the blue and red inks. Okay. We're I was thinking about doing this as a discussion board, this page. I might still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That'd be half the class. Yeah, we'll call this our discussion board with the first one already done for you, so no one's going to do that one. So this will be our discussion board for the day that I'll set up later this afternoon. For each of the following conversions, write down the equation representing the proportional relationship. Now, yes, proportional relationships we've said classically is fraction equal to fraction, but we've also said we can use a y equals kx setup. So that's what these are relating to. So first they say 1 centimeter is 10 millimeters. So if you had 2 centimeters, that would be 20 millimeters. If you had 3 centimeters, it would be 30 millimeters. If you had 10 centimeters, it would be 100 millimeters. It's just the number of millimeters, which they call m, is equal to 10 times the number of centimeters. This right here is just the k, the multiplier. But what you have to make sure, though, when you're doing this in your discussion board, is that you get these letters in the right place. Because if you wrote c equals 10m, this would be wrong, because no, it's not the number of millimeters times 10 gives you the number of centimeters. Just think about, all right, if 1 is 10, what would 2 of these be? It would be 20. And then think about yourself plugging those numbers into this equation and seeing if it would get it the right way with what I have crossed out or with what they have in black ink. Now, the letter choice that each student makes could be different, especially for this one right here. They both have F, so maybe you use L for furlong or G for furlong, and F for feet or T for feet. So maybe when you're doing your discussion board, you could use your words and use your letters. So let me just make up a fake one. This is completely fake. Let's say that I said 1, I don't know, calculator was equal to 7 oranges. What would the equation that I could write out be? Well, 1 calculator is 7 oranges, 2 calculators would be 14 oranges, et cetera, et cetera, et cetera. So the calculator is the thing that needs to be on the other side, then I multiply it by that to get the bigger number. So I'll call oranges, I'll use the letter R, and then that would be equal to 7 times the number of calculators, and I'll use C. So that's the equation I would write, and then maybe I spell out in words that the number of oranges is equal to 7 times the number of calculators. So you can use your words, you can use abbreviations, or you can do both. I would love to see each student write it in both, but if you only do one or the other, I still give you full credit for that. So this is an opportunity for 12 students. As I said, not all discussion boards give every student an opportunity. Remember, all students do not have to do every single one of them. It's just I have to see, participate in, we say most. And most is objective or subjective. Subjective, definitely subjective. So most by the end of the semester could end up being half of them. It could be 2/3 of them. It just depends on how many discussion boards I gave you where everyone could participate or only like 10 people could participate. So take every opportunity you can. If for some reason you just have bad timing and you're going up there every time to do something, talk to me and be like, hey, Mr. Beckner, I kept going in. I was just going too late. I never got any opportunities. We can work something out. All right, so again, this is 12 single student opportunities. Now, again, if a 13th student comes in and says, well, I think this person did something wrong, then they can make a comment and set it up how they believe is correct. And then maybe another person comes in and says, no, I think person A was right, or no, I think person B was right. But have a discussion, don't just type 3 words. All right, so let's clear that. And we're going to do some of these in number 2. We're not going to do all of them. We don't have that much time. And let's do this. Let's do this. Let's set up a new one. So hit enter 10 million times for some space. All right, so for number 2, this is on page 118. This is not discussion board. This is not discussion board. We're going to convert 6 feet to meters, and they give us this table above to use for problem number 2. So we start with 6 feet, and we're going to multiply by a fraction, maybe 2 fractions, maybe 3 fractions, we'll see, in order to go from feet to meters. So we've got to look at this chart and see, first of all, are there any of these that go directly between feet and meters? And if there are, that's awesome. If there aren't, then we're going to have to middleman this and say, all right, well, we need to go from feet to something, and then from that something to meters, hopefully. And it may take you 2 of those. It may take you 3 of those. We will see some examples of that. All right. Unfortunately, I can't see everything on the screen, so I got to scroll up. There we go. That's good for now. Like I said, I have some hidden menus that you can't see. So let's see, feet to meters. Well, this third one, 1 foot is 0.3048 meters. So that would go from feet to meters. And you could certainly use that one. But check this out. There's another one. There's right here. 1 meter is 3.281 feet. So let's pull up annotate. For problem A, I'll put the A there afterwards. We could use this conversion, or we can use this conversion. You might say, why on earth are there 2 of them? Why wouldn't somebody just make 1 of them? It's all about what is scaled to 1. So if we're starting in meters, it would be better to use the top one because we could just have a simple multiplier. But if we started in feet, it would be better to use the bottom one because then we have our simple multiplier. However, it doesn't technically matter which one we use, whether we go with a simpler or more complicated one, because of dimensional analysis, it absolutely doesn't matter. All right, so which one do we want to use? I'm going to do the bottom one. So I'm going to go 1 meter is 3.281 feet. So I don't even need to look at this for now. I'm not going to look at these at all. It's just I know I got something going between feet and meters. So over here, because the feet were in the top and I need to out with the old, the feet will go on the bottom. Now I got to clear my screen so I can use this more properly. I know that was weird. I know that was weird. Okay. Feet, bottom, and our new units, which we know we can convert directly to, are meters. So again, if I did the top one, I'm going to use blue because this isn't the one I'm going to use. I would put the 1 in the bottom and the 0.3048 in the top. And this would give me an accurate answer, and I'll even show you, I'm going to erase all this eventually. So the feet will cancel, and we're going to take the 6 times the 0.3048. 6 times 0.3048. 3048. And we get 1.8288. They said to round to 2 decimal places, so that would make that 1.83. So I'm just going to write this over here. And then we know the units are meters because that's what was not canceled. But instead of using that one, let's use the other one. So that's the answer we got with using row 3. Let's go back to row 4, 5, 6, 7. That 1 meter is 3.281 feet. So now the 1 goes with the meter this time, and the bottom one is a 3.281 feet. Feet will still cancel. Now, because that 3.281 is in the bottom, we're not going to multiply, we're going to divide. See, that's the big difference here. 6 divided by 3.281. Now, I'm going to spoil something. No, I won't. Let's look at the answer. I was about to spoil it, but no spoilers. The first time we got 1.8288, this time we got 1.8287, blah, 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 blah. This is because these conversions are all rounded. It is not exactly 0.3048 meters. It keeps going and going and going, but no one wants to write 10 or 20 decimal place for a unit conversion. But the cool thing is when we round to 2 decimal places, look at this, 1.82, the 8 says round to a 3. We get 1.83 meters. The same answer as doing it the other way. So it didn't matter which one we used. Maybe you only saw the top one. Maybe you only saw the bottom one. But if you saw both, don't freak out and say, which one do I use? It doesn't matter as long as you put the numbers in the appropriate place. As long as you put your out with the old and with the new units in the appropriate place. That is the wonderful thing about dimensional analysis. There can be so many different ways to do things, or just unit conversions in general. I could have done this as a proportion, as we've already said. I could have also set this up. So remember, your discussion board is going to be to write these equations. If you pick the easiest equation out of the 3rd row or the 7th row, you could just put the 6 in there, multiply it by the number, and you'll get about 1.83. But I don't want to spoil that since it's a discussion board answer. So if between row 3 and 7 using the equations you'll set up, one of them you would actually have to divide both sides to solve the equation. The other one is just going to be staring you in the face. All right, 64 inches. We're going to convert this to feet. Well, I hope you don't even need this table. I hope that you know that it's 12 inches as a foot. So I'm going to do 12 inches in the top and 1 foot in the bottom. Question mark, question mark, question mark, question mark. No. I was trying to rush intentionally and doing this wrong intentionally, but this isn't always going to be so obvious to y'all. Why is this wrong? My out with the old, in with the new isn't going to work. They're not going to cancel. Now, if you're just rushing and you go, oh, I know the answer's feet and 64 times 12 is big number, and then it's going to tell you you're wrong because you're rushing. You're not being fluid and careful with this. We set up the multiplier upside down. To out with the old, inches must go in the bottom and the feet must go in the top. And then, oh, 12 in the bottom, 1 right. Nope, that's wrong. Or is it? Ha, 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 ha. Yes, this is correct. I was just messing with you that time because I did the first one wrong, so I wanted to play with you a little. But again, these are the things that you might start doing in your head. Oh, no, it's probably wrong because I did it wrong the first time. I'm going to keep doing it wrong. No, you can't have the mindset. But checking things and make sure, oh, yeah, the inches are good, and it is 1 foot is 12 inches. Those cancel, and you're just doing 64 divided by 12. So we'll want our calculator for that to make things easy. 64, oops, 4 divided by 12. It's like 5.3 bar, I think. Yep. So 5.33333 or 5.33. What are our units? Feet didn't cancel, so they're in feet. There we go. C. All right, we got 350 centimeters, and we want to convert this to feet. So I don't expect anyone to know this off the top of their head, how many feet is how many centimeters. So you would go to this table again. So we're going from centimeters to feet, so 350 centimeters to feet. Why would you want to convert centimeters to feet? Well, maybe you've got to deal with someone else and they've measured in feet and you've measured in centimeters, and it would just make more sense if you're both in the same units and the other person has higher rank on you, so you got to change your units to theirs. Something like that. Okay. All right, centimeters to millimeters. Well, I don't think that's going to help us, is it? Inches to centimeters. Well, okay, centimeters to inches. That might be helpful, but we're supposed to be going to feet, so that's not direct. Centimeters to meters. I don't even see any other centimeters. So there is no direct conversion from centimeters to feet in this table. Again, yes, Google could get you that direct conversion, but we want to practice this multiple layers concept, so let's pretend Google doesn't exist. So we at least know for our first multiplier, we absolutely have to get rid of the centimeters, no matter what, no matter how many times we're going to do this, out with the old, in with the new. So what are some good options here? We're going to go from centimeters to some middleman to eventually get to feet. So we got to find a middleman that hopefully has feet in it. All right, centimeters to millimeters. I just have a bad feeling it's not that one. 1 inch is 2.54 centimeters. Well, centimeters to inches, that might be a good middleman because we know how to go from inches to feet. So that's a good one. We also have centimeters to meters and meters to feet. So these two paired together could actually benefit us as well. So you could use these two, or we could use the, again, 1 inch is 2.54 centimeters. And then do they actually even put it in here? Yes, 12 inches is 1 foot. So you can use these two paired together, or you can use these two paired together. It doesn't matter which ones you use. There are always going to be multiple paths to a destination if there's a middleman. You just have to be able to connect the dots. So I'm going to go with the top one. I'm not going to show the second one. You can certainly do it on your own if you prefer, and you will hopefully get the same answer as us. So we start with centimeters, so we got to go centimeters to inches, centimeters to inches, and we said it's 1 inch. Oops, I'm mixing. Clear my screen now. Come off of annotate, so inches. It's always weird when that happens. 1 inch was the 2.54 centimeters. So that'll get rid of the centimeters, and now we're in inches, but we're supposed to be in feet, so we go from inches to feet. Out with the old, inches go on the bottom, in with the new, feet go on the top. And it's 12 feet is 1 inch, right? Question mark, question mark, question mark. See, last time I was messing with you and it was fine. This time I'm messing with you and it's not right. 12 feet is not 1 inch. Make sure. Okay, yeah, 12 and 1 are the numbers to use, but I put them in the wrong place. 1 foot, 12 inches. So the inches cancel. And we're just doing 350 divided by 2.54 divided by 12. When the numbers are in the bottom, you divide. When they're in the top, you multiply. 350 divided by 2.54 divided by 12. And we get 11.48 feet when we round to the nearest tenth. 11.48 feet are the only units left. So feet is the answer. And I think this answer makes sense. 350 centimeters. A centimeter is a smaller unit of measurement than a foot. A foot is definitely bigger than a centimeter. So more centimeters, it'll take more centimeters to make less feet. Same thing up here, 64 inches. Inches are bigger than feet, so there should be less of them as feet. Feet are smaller than meters, so the answer in meters should be bigger, should be smaller as well. All right, D. Scrolling, scrolling, scrolling. 149.6 kilometers, and we want to convert this to miles. I just want to put MI above this so I don't have to keep thinking about that and memorizing it off the top of my head. 149 kilometers, and we're converting these to miles. So again, there is no direct miles to kilometer up here, is there, right? Question mark, maybe I'm misleading you. Let's see. All right, let's see what else got kilometers. No kilometers, no kilometers. See, I'm just hunting for anything that has kilometers. Oh, we got a kilometer, we got a kilometer, we got a kilometer and a kilometer. So there's the 4 things with kilometers. Kilometers to meters might be helpful. Kilometers to miles, well, actually, yeah, that one's perfect right there. Miles to kilometers, this one's also perfect. Kilometers to nautical miles, we definitely don't need that. We don't need to go to nautical miles to get to regular miles. And in fact, there are no other nautical mile conversions up here. So that's a dead end for that last one, unless we were just converting to nautical miles, which I've always just said it's about 2 kilometers per nautical mile, roughly, because 1.8 is close enough to 2 for government work, right? All right, so we can use the 0.6214 miles value or the 1.609 kilometers value. I'm going to choose to use the top one since no reason, I'm just going to use the top one. It's the one I saw first. So this is the one I'm going to use. That 1 kilometer is 0.6214 miles. If you don't believe me that they work both ways, do the other one. I know I hit red. So out with the old. Kilometers must go in the bottom even before even looking at any of that stuff. We know we have a direct conversion to miles, so there we go. So I can go 1 kilometer in the bottom and the 0.6214 miles in the top. Or I could have done it this way. I could have used the 1 mile as 1.609 kilometers, so km in the bottom, miles still in the top, but now it's 1.609 in the bottom and 1 in the top. You'll get basically the same answer when rounded to the nearest tenth afterwards. Only going to show one of these, the 149.6 times 0.6214. Hit enter, your kilometers cancel, and you'll get 92.96 miles, and you'd get the same answer the other way. Now, let's say you didn't have a calculator. Let's say you're stranded on a desert island doing your math for some reason, or your calculator's dead and you still have to do this problem. It died during a test. Which way is easier without a calculator, the top way or the bottom way? What do you think? Which one would you rather do by hand? And I know you'd rather do neither by hand. I already know that. But would you rather do this way by hand, having to hand calculate all those numbers, or would you rather do this way? And for me, this is the easier way. This is the easier way by hand. I'm going to erase these little memos in a second. And here's the reason, this is the entire reason, this is a multiplication of 149.6 times 0.6214. Would you rather multiply decimals or would you rather divide decimals? That's what I'm talking about easier. By hand, I would much prefer to multiply decimals, especially when we're dividing by a 4-digit number, 1609. Good gravy. That is not a fun division to do by hand. The multiplication, yeah, it's 4 digits and 4 digits. It's going to be a little time consuming, but it's just doing single digit math over and over and over and over versus 4-digit division. It is going to make us want to cry by the end of it. So that's one of the benefits to having choice. If you don't have your technology, if you don't have your calculator, if you're just doing this by hand for whatever reason, I would choose the top way versus the bottom way because it's multiplication instead of division. Just makes it easier. All right, E, and this one's kind of interesting. And by interesting, I mean you can do it a way that's not even in the table. We're converting 1,000 millimeters, and we want to convert this to M, which is meters, not miles. So some of you will know, at least one of you will know, I hope. Some of you would know, I hope even more, that there's 1,000 millimeters to a meter. That is nowhere in this table. So I'm not even going to use this table. I just happen to know that 1,000 millimeters is 1 meter. That is the entire basis of that system of the, sorry, had an itch. Of the much better system of tens, in fact. The system of 12 inches is a mile that is very, very old and archaic, and America actually tried to get rid of it in the 70s or 80s and failed miserably because we're just stuck on what we know. It's a lot easier converting in the metric system because meters to kilometers, you just divide by 1,000. You just move a decimal 3 places. Going from millimeters to meters or meters to millimeters. It's just moving decimals. It's much simpler. But you can still do this fraction multiplier stuff. So I happen to know, again, out with the old, in with the new, that it's 1,000 millimeters is 1 meter. So I didn't even pull this from the table. I just knew that the thousands will cancel, the millimeters will cancel, and you'll end up with an answer of 1 meter. But using the table, again, this was my brain, using the table way, which was not written, you start with your 1,000 millimeters, and you'll have to multiply by a fraction. Out with the old, the millimeters are definitely going to go in the bottom no matter what. And let's see, we could use, well, here's something with millimeters. Is that the only one? Making sure I'm just not blind today. Millimeters, that's the only one I see. So that's what we'd have to do first. We'd have to go from millimeters to centimeters. So we'd say that 1 millimeter is 10, whoops. Where's my mouse? Annotate that 1 millimeter is 10 centimeters. So we'd be, I wrote that upside down. I was thinking 2 steps ahead. It's not 1 millimeter is 10 centimeters, is it? It's 10 millimeters is 1 centimeter. See, by paying attention and checking myself, I was about to make an error and I caught myself. It wasn't even one of my little silly play arounds. I was about to make an error. Okay, so your millimeters are gone. And you could simplify this if you wanted to, but I just like going ahead and showing all the multiplier and stuff now. But now we're in centimeters. So let's see if there's something that'll take us from centimeters to what we want as meters. Let's see, annotate. Centimeters to meters. Well, here's centimeters to inches. That's not optimal. Not seeing centimeters. Oh, here we go. Centimeters to meters. That's exactly it. So 100 centimeters is 1 meter. So we go off of annotate. 100 centimeters is 1 meter. And when you end up doing 1,000 divided by 10, you'll get 100, and then divided by 100 is going to give you 1, and the meters will be the only units left, so you get 1 meter, the same answer. So again, this top version, while I said it's in my head, if you went to Google, Google would tell you that. So like I said, there is always more than one way to do these problems, even for the ultra simple ones. There's still more than one way to do them because you could extend them if you really wanted to. Let's do F. I really do love these problems. I know that sounds sick, but that's me. F, let's clear my screen. That's weird. It didn't clear. There we go. Oh, I know what I did wrong. All right, 3 miles to meters. 3 miles to meters. Again, the little thing in parentheses is just saying what I'm converting to. So if there's something above that goes directly from miles to meters, that would be awesome. Google would probably have that as well, but we're going to ignore Google. We're just going to go with the table for good practice. So let's see. Miles, 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 miles. I'm just hunting anything down that's got miles. Miles, miles, miles. Here's a miles, and here's a miles, and here's a miles. So we got kilometers to miles, we got miles to feet, and miles to kilometers, but none of those are meters. Well, that's slightly annoying, but that just means we'll need another fraction. So I want to go ahead and connect the dots. I got to decide what my path is before I start doing things, otherwise I could dead end myself. So if we go from miles to kilometers, let's say I chose this one, and there's 2 options. Here's miles to kilometers, here's miles to kilometers. So it doesn't matter which one I choose, but let's say we went from miles to kilometers, and I happen to choose, which one am I going to choose? Maybe I choose the top one. I don't know. Then you could go from kilometers to meters using, where is it? Right here. There's kilometers to meters. So I could do this first, or I could do this first, and then this would be second. That's one path. Another path, which I'll do in blue, I could have chosen the 1 mile is 5280 feet, so this could be a first and another alternative path. So we're going from miles to feet. Now we're going to see, is there anything that goes from feet to meters? Feet to meters, feet to meters, feet to, oh, here we go, feet to meters. Was there another one, or is that the only one? There's another one. So either of these would be second. So you have two options for the first in the red path, and then only one option for the second. Or you could do only one option in the blue path for first, and then you have options for the second one in the blue path. So there's definitely options. So let's see, that's 1, that's 2, 4, that's 8 different ways that this problem can be solved just using this specific table. In the real world, there's millions of ways. So I'm actually going to take the blue path. This is the choice I made. So I'm going to take the blue path. So first, I'm going to go from miles to feet. So I'm going to multiply. Got to have miles in the bottom no matter what. Feet will go on the top. 1 mile is 5280 feet. I feel like this is a number that some people know. I definitely know it. I don't make you memorize it, as I've already said several times, but it is a good one to know. So the miles will cancel. And I'm not saying red and I'm switching paths. In fact, for this one, I'll stick to blue. So there's just another multiplier. Now we got to go from feet to meters. And we said we could use either of these, that 1 meter is 3.281 feet or 1 foot is 0.3 blah, blah, blah meters. But we know the feet go in the bottom, the meters go in the top. I'm going to pretend like I was doing this by hand. So I want the number to be in the top. That means I want the 1 foot in the bottom. So I have to use this top option over here, the 0.3048 meters. So that's the way I chose to do things, just so I'm multiplying things because that would have been the easier way to do it by hand. All right, so we start with our 3 miles. We multiply by 5280, which is 15,848. And then we're going to multiply by, I don't know why I had to hit enter there. I usually don't, but that's okay. And then times the 0.3048. And you get 4828, blah, blah, blah. So 4828, and they set around to the nearest tenth. So 0.03, and the feet are canceled, so the only thing we're left with is meters. And that would be our answer, 4,828.03 meters. Now, I will mention with this problem that if you did a different path, it will give a slightly different answer. Maybe like 4827.9 something. So remember how we had an example earlier where it was like in the thousandths where the numbers were different because of the different path we chose to take due to these things being rounded? This 0.3048 is rounded. If we'd done the other option in blue, the 3.281 is rounded. So using a different option gives you a slightly different answer, and with bigger numbers, the answer will be a slightly bigger error. So this one's off, by a couple of tenths, but it's not the end of the world, or maybe just 1/10 really. The cool thing about MyMathLab is they accept a range of answers for problems like these. So they have a tolerance. They know that based on the different paths you could take, maybe you get the 4828 or maybe you get the 4827. And you might be a little frustrated because we just had this quiz where I lost a point because of my rounding error. That's not the same thing. That was a mistake. This is not a mistake. This is just getting different answers due to rounding in unit conversions that, again, is accounted for in things like homeworks and quizzes. All right, got 5 minutes. Let's do G, and that'll be, we won't do H. Clear my screen, annotate, clear, boom. G, 149.6 million kilometers. So I'm just gonna go million kilometers. And what you could instead do is just move this decimal 6 places to the right and have a whole bunch of zeros. And we want to convert this to millions of miles. Well, we have direct conversions from kilometers to miles. But you might be saying, well, we don't have a conversion from millions of kilometers to millions of miles. Doesn't matter. The word million is just going to stay tagged along with. That's all. So we'll multiply by a fraction. And I'm going to use the one that says 1 kilometer is 0.6214 miles because that'll put the goofy number in the top. So I know out with the km, out with the old, in with the new, miles. So I'm going to pick the one where I want the 1 in the bottom and the goofier number in the top. Again, that entire train of thought is just, if I was doing this by hand, I could do it by hand easier. It would not be wrong to have chosen the fact that, where is it, 1 mile is 1.609 kilometers. You just have a 1 in the top and a 1.609 in the bottom. And when you multiply that 149.6 times the 0.6214, we'll get 92.96. And then your kilometers canceled. And some people might do this. They'll say it's miles. That's wrong. Because we have a unit in there that we did not cancel. That was the millions. So it's not miles. I'm going to maximize this for full space. It's million miles. Or 9296000000 miles. Those would both be acceptable. If you look at G and you compare it to D, 149.6 kilometers, 149.6 million kilometers. The math was literally the exact same that I chose to do the multiplier. The number was the same. It's just the units, instead of being miles, were millions of miles. So you don't have to put all those annoying zeros up there and deal with the answer that way. When you have words in millions or billions or trillions or hundreds of thousands or whatever, you can just attach those words as long as they're consistent. Spoilers for a later group work activity thing, we're going to start seeing some things where they aren't consistent, like one thing will be in millions and another thing will be in billions. So the idea there is just convert one from the other first and then start proceeding, or just give everything the appropriate number of zeros if you prefer that. Either, perfectly fine. Okay. So, yeah, we can talk about it. We got the time. We have just enough time. Temperature conversions, the last topic of the section. So we will close out this section. I might do 1 or 2 more examples of this next time, but I will say that we finished the section today, and the homework is going to be due in a week when I write my notes at the end. Temperature conversions work differently. Temperature conversions are drastically different from converting feet to inches to meters, or from seconds to hours to days, or gallons to kiloliters or liters or whatever, anything like that. Temperature is its own unique beast. And the entire reason is because 0 degrees Fahrenheit is not the same as 0 degrees Celsius. In order for two things to be proportional, 0 and 1 has to be 0 in the other. That way, if you double one, the other doubles. Temperature doesn't work that way. 32 degrees Fahrenheit is 0 degrees Celsius. 0 degrees Fahrenheit is some negative number in Celsius that I don't know off the top of my head. Somewhere in the ballpark of 15 to 20. I don't know. No one ever memorizes that. So because 0 and 1 is not 0 in the other, you cannot treat these as proportions. You cannot do dimensional analysis with this. You must use conversion equations. You have to use conversion equations, and I will not make you memorize these. These will be given for a test. And in particular, the one that we stick with is C equals 5 over 9F minus 160 over 9. That's a good one. You can also say that F is equal to 9 over 5C plus 32. These are the two conversion equations. There are alternative versions of them in decimals for the 9/5, that's 1.8, or you can factor out the 5/9, and it's C equals 5 over 9 parentheses F minus 32. Again, F equals 1.8 C plus 32. All four of these are the same thing, just algebraically rearranged or numerically rearranged. 9/5 is the same as 1.8. This bottom thing is the same thing as the top thing with just the 5/9 distributed, because 5 times 32 is 160. Again, you don't have to memorize. I would give you only one of these on the test. It may be this one, it may be this one. So you have to understand your algebra with these. It's nothing too crazy though. So what we'll do for the last bit, and again, I will do at least one more next time because I'm only gonna have time to do one of these. Let's do 1A from the guided activity. On another page, obviously, page 122. Weird. Technology, always fun. Okay. So we're going to convert 40 degrees Fahrenheit to Celsius. 40 degrees Fahrenheit to Celsius. So 40 degrees Fahrenheit to Celsius. There's no fraction multiplier. There's no cross multiplying. There's no dimensional analysis. You have to use one of those equations. So I prefer the one that looks like C equals 5/9 parentheses, and then it's F minus 32. How do you know where this 40 gets plugged in? Do you plug it in for C or do you plug it in for F? Well, it says F, so plug it in for F. It's as easy as that. So we get C equals 5/9 times 40 minus 32, which is C equals 5/9 times 8. 5 times 8 is 40. 40 divided by 9, and you wouldn't have had to have done that middleman step if you didn't want to. 40 divided by 9, please turn on calculator. My batteries are dead, I guess, ha ha ha. 40 divided by 9 is 4.44. 4.44, now we know we're in Celsius, so it's 4.44 degrees Celsius. So 40 degrees Fahrenheit is equivalent to about 4 degrees Celsius. Then you say, does it make sense? Well, yes, because 32 degrees Fahrenheit is 0 in Celsius, 40 is close to 32, 4 is close to 0. So I'd say that makes sense.
Just setting up for the next section. All right, so when I stopped the video, there was going to be a part B, and it doesn't say B on the screen currently because things got messed up, but this is part B, just so you know. So again, this will be our last question with temperature, then we'll actually get into the next section. But again, just one more temperature example, and here we go.
So what is 212 degrees Fahrenheit in Celsius? Now you may know this answer off the top of your head. That's not the point of this. The point is plug it into an equation and see if you can get the answer. Now, since I gave you a temperature in Fahrenheit, you have to plug it into the F because that represents the temperature in Fahrenheit. So you could either plug it into this equation there, which means you're going to have some algebra to do. You'll have to move the 32 and get rid of that 9/5 somehow. Or you can plug it into this one, and then all you got to do is arithmetic because the C, the temperature in Celsius, is already by itself. So what that means is that for this problem, it's easier to plug it into the one that says C equals instead of the one that says F equals. You can get the exact same answer either way, but the right-hand one is going to be easier. So we'll get C equals, excuse me, 5/9, parentheses, 212 minus 32, and then you close your parentheses. If you do 212 minus 32, you're going to get 180. So you get C equals 5 over 9 times 180. Now, yes, you could go ahead and put this in a calculator, but I've also mentioned that you're supposed to know your math with fractions, so you can reduce the 9 and the 180. 9 will go into 180 20 times, so you can say 9 goes into 9 once into 180 20 times. And then you're just doing 5 times 20, which is 100. And you get C equals 100. Now, again, this is not an answer as a quantitative reasoning student. You don't say it's 100 degrees. You don't, first of all, you don't say it's just 100. Second of all, you don't even just say it's 100 degrees. You would say it's 100 degrees Celsius. That's the answer as a quantitative reasoning student. Hint, wink, nudge towards something I just mentioned that you have to answer as a quantitative reasoning student. I didn't just say 100. Hint, wink, nudge. Now, spoilers, the answer in your quiz, or the question in your quiz has nothing to do with temperature, so you don't worry about like, well, how do I put this little degrees symbol in Canvas? Don't worry about that. It's a much simpler idea there. So that's temperature conversions. Again, we said that temperature conversions are not proportions. So the idea of dimensional analysis, which is what we heavily focused our ideas on in 3.1, does not work. You can't just say out with the old and with the new. You can't multiply by a fraction where your old units are in the bottom and the new are in the top. It does not work because 0 degrees Fahrenheit is not 0 degrees Celsius. So the whole idea of one thing doubling and the other thing doubling falls apart. All right. Also, that means you can't use the proportions version of it. These aren't inversely proportional either. It's nothing to do with proportions. Temperature conversion is just a fancier formula. And this idea right here, especially with the F equals, this is something we're going to start studying a little more heavily in chapter 5, where you've got a number paired with a variable and then another number just by itself. This is what we call a linear model with a fixed amount and a variable amount, but we'll save that discussion for another day. And the idea starts with proportions here. This part, if we only had that part, then it would be proportional, but it's the 32 in this instance that makes everything not proportional. So I had said that some of you may have known that 212 was already the answer, which is 100 degrees Celsius, because that's just one of the two conversions that actually established the equation. When someone decided to make Celsius, because Fahrenheit was the OG in this instance, they said, all right, we want to make the water freezing temperature of 32 degrees Fahrenheit. We want to make it 0 degrees in this new thing for simplicity. And then when water boils, which was traditionally 212 degrees Fahrenheit, we want that to be 100 degrees for simplicity, because Celsius, like every other European conversion, meters, liters, all that stuff, they're all based on powers of 10, because powers of 10s are easier ultimately because we count with our fingers and toes traditionally, and most of us have 10 of each. So that's actually the entire reason we have a counting system based on 10. If all of us were born with 8 fingers and 8 toes, we would count 1, 2, 3, 4, 5, 6, 7, and then it would be 10. There would be no 8 and 9. And then we'd go 11, 12, 13, 14, 15, 16, 17, and then we'd be at 20. And that sounds really freaking weird, I know, but that is the entire reason we count in tens. It's because it's what we have on us, traditionally speaking. All right, so that's 3.1. 3.2. And if you are actually going into these notes and reading ahead like you're supposed to, which at this point, I have no idea who is. I think I probably need to do a quiz ahead of time on that at some point soon. It seems like a good idea. You will have noticed that 3.2, I hardly have anything typed in this. It's 3.2, it's 4 or 5 lines, and then 3.3. So this is a pretty short section. We will still have a nice little, we'll pull something from the guided worksheets, which let me go ahead and open that up. I did not, I was fighting my computer this morning, so I didn't have time to open this, sign in, and get those worksheets open, and then we'll start our talk. Maybe we'll see the guided worksheets. I might just have to write them up. Luckily, I have the printed version in front of me. All right, cool. There we go. All right. So scales, wrong thing. Scales. A model scale is a ratio. Oh, look, ratio. We spent all of chapter 2 dealing with ratios. Well, I would say like 85% dealing with ratios because uh, inverse proportions are technically not a ratio when you set them up accurately. If you set them up inaccurately, they can be a ratio, but that's a horrible idea, and don't do that. Um, but that's inverse. Notice I said inverse, not direct or not just proportions. Attaching inverse changes the game. So most of chapter 2 we spent dealing with ratios. Back in the last section, we were dealing with proportions, which are just ratios. We learned dimensional analysis, which was just another way to handle proportions. Huh, interesting. So a model scale, the stuff in 3.2, is more ratios. Everything in chapters 2, 3, and 4 is based on the concept of ratios. When we get into chapter 3, ratios are still a part of everything, but there's something else going on, and I already alluded to that a few minutes ago when I was talking about that plus 32 thing. So these ratios, they don't go away. They don't go away. This one topic is the basis of probably 3/4 of this course. So it's a ratio used to determine the size relationship between a model and what it represents. So when you open your GPS and you see the map going from your home to your destination of wherever you're going, if you're going anywhere in this world right now, um, on your screen, it only looks like maybe 2 inches, but in reality, you might be going 17 miles. So there's a ratio involved there to scale the quantity of your actual distance to the distance on this map that represents everything that everything that you'll go in terms of driving. So a scale is just a ratio. So it might say something like, all right, well, 1 mile in reality is 1 inch on your map. That would be a scale. Or maybe 2 miles in reality is 1 inch on your map. Or maybe 3 miles in reality is 7 centimeters on your map. It doesn't have to be inches. It doesn't have to be miles. It could be 10 kilometers in reality is 14 inches on your map. They don't have to be ones. They can be anything. Usually we like one of those to be a 1, which is why I say the word typically. And then when I say typically, the first quantity is scaled to 1. When we say first, we're typically referring to the model. So again, this is typically, this is usually, this is almost always, but not always. So usually it's like 1 inch on the model, and then that might be 3 miles or 5 miles or 10 miles in reality. Or 1 centimeter in the model is 3 miles or 5 miles or 10 miles in reality. And again, there would be only one of those things. It just depends on how everybody set it up. And it doesn't have to be maps. When you talk about model cars and planes and action figures, if they're super realistic in terms of proportionality, then you can use this model scaling the same way. Say, oh, okay, well, I've got this car that's normally, I don't know, about 12 feet long, and the model's going to be 1 inch long. So that would be a 1 to 12 model. 1 inch is 12 feet in reality. And that's a pretty small model. That's like a micro machine, I guess, if they still even make those. I have no idea. If you don't know the reference, I'm sorry. Then there's bigger toy models. So maybe it's like 1 foot is 12 feet. So 1 foot of the model, which would be a larger model car, would be 12 feet in reality. Or maybe you've got a model airplane. So a small airplane here. So 1 inch is 72 feet on the airplane, maybe, or 1 foot in the model is 72 feet on the airplane. So there's no units written here. So that's saying it could be the same units, 1 inch is 72 inches, or it could be different units, 1 inch is 72 feet. So again, typically the model quantity is scaled to 1. So when I say first here, first I'm saying is the model, the smaller of the two things, because when we make a model, we generally going to make it smaller. Why would you make a model that's bigger than the actual thing? Now, yes, there are cases where that's true. If you have something ridiculously teeny, if you're trying to make a model of, say, an atom, then you're going to increase the size. So maybe I don't want to use the word that it's rare, but it is less often, I feel like. Usually we're scaling things down, but there's certainly instances where we want to scale them up. Okay, so this 1 to 72 is a pretty common scale. 1 to 48 is also another common scale for models with like little toy planes and cars and things. That's not something you have to memorize. We would give you the scaling factors. That's what we call that constant of proportionality, which in this instance would be the 72. It's a 1 to 72. That's the scaling factor. The cool thing is, if you don't like setting up proportions where you use your words and then write the scaling factors on the other side, you can also set up a y equals kx proportion form instead of writing it fraction equal fraction. You can do this instead, and the k is that, as long as you have the actual on the left and the model on the right, unless it's the flip-flop where you're scaling something up, like a cell or an atom. And I usually have a joke that goes with that, and I'm not going to say it. Again, I'm always a little weird about my jokes, whether I want them recorded on the internet, if they have even just a touch of, you know, what's the word I'm looking for? They're not G-rated, I guess. They're PG, but even still, you never know what'll happen 10 years from now, and I get canceled. Okay, so let's try this stuff out. Let's see how we can actually use this. And let's go big. Literally, let's zoom in and go big. No, not that big. And I'm going to, yeah, let's open up a new file. Give myself some space. That way we can do this and this. Perfect. You wish to create a scale model of the solar system. Let's maximize it for now. On your campus quad, when you're allowed to go. Well, you can still go there. You just don't go in the buildings that much. You can still go in there, I guess. That is circular and measures 240 yards in diameter. So what they're saying here is you've got a quad that is circular. It's not too often that quads are circular, but that's okay. But maybe your quad isn't circular. Maybe your quad is a rectangle and it's just the model you're going to build inside of it is circular. That would be another way to rationalize that too. And it makes a little more sense that way, in my opinion. And it measures 240 yards in diameter. So we've got this circle, and the diameter, which is the distance from end to end going through the center, that's 240 yards. Okay, so that distance is 240 yards. And we are going to fit the entire solar system into this circle, and we're going to use these given values, which are true as far as I know. I've only checked a few of them because I figure if the first three are right, then the rest are right. But you know, don't take me to the cleaners over that checking. So they say that Mercury is 57.9 from the sun. So when they say orbital radius, that means how far it is from the sun. Now they have planet Pluto. Pluto is not a planet anymore. Also, it doesn't have a circular radius, so there's a couple of minor issues there. It's also on a tilted axis. So I mean, you could just say, well, Pluto's not a planet. We're going to ignore it, but let's not get into all that science and stuff. We're gonna go and pretend it's still a planet, I guess. All right, so Mercury is 57.9 from the sun. 57.9 what? That's not a QR answer. Oh, millions of kilometers, not just kilometers, millions of kilometers. If Mercury was 57.9 kilometers from the sun, it would probably just catch on fire and just be eviscerated. That's what I was trying to say. So Mercury is 57.9 million kilometers away. Venus is 108.2 million kilometers away. Earth is 149.6 million kilometers away. So we can see that these planets are getting further and further away from the sun. So they are in order, in that traditional order of distance from sun to furthest out. So what they will say is we want to create a scale model of the solar system on the quad that is circular and measures 240 yards in diameter. And we are going to scale Mercury to 1 yard. This is our decision. We said, all right, in this, we want to make, let's say our center is right here. We want to put Mercury, I know Mercury is not green, bear with me. We're going to put Mercury right here. And this distance right here is going to be 1 yard. And then here is its orbit. And then Venus is going to be some distance further away. So maybe Venus will do in this little dark red. So maybe Venus is over here, a little further away. I'm just going to go V for Venus. Here's its radius. And then we're trying to figure out what this distance right here would be. That is what would go here. That's not 0. I'm just saying it's what would go there. And then we're doing the same for all the rest of the planets. Now, I'm not going to fill all of these out. I'm only going to do a few of them. I might leave this for a quiz. I might leave it for nothing. I might just say, hey, I would highly suggest that you finish this on your own and be good students because it's excellent practice. That's probably what I'm going to do in this instance, since I already have a quiz assigned for today and I don't like going back. Okay, so if you set Mercury to 1 yard, what is the model scale you are using? So what they're asking has everything to do with Mercury and will end up being used throughout the rest of the planets. Now, before we move on, actually, I just need to clear my screen. Go, we're off of annotate. Okay. So here's what we want to do for the scaling. The two things we're talking about are the model and the actual. The model and the actual. So the model's distance and the actual's distance. So we have our model and then the actual. You can even be super specific and say the model is in yards and the actual is in millions of kilometers. All right, so these are the words, and then we just use up the numbers. Well, for the model, we said it was going to be 1 yard. So where does that go? That goes in the top. So the 1 yard goes in the top because that's what we determined, what we decided the model distance should be, and we're hoping that everything's just going to fit in this 240 yards. All right, well, what was the actual distance to the sun? The actual orbital radius, same thing, 57.9 millions of kilometers. Well, there we go. So what is the model scale? It's 1 yard is 57.9 millions kilometers. That is the answer to A. Because when you use your words, apples over oranges, and then every 1 apple is 57.9 oranges, again, you don't have to think about these things in terms of anything complex. You can just always relate everything to apples and oranges, thing A and thing B. So that's the scale. For every 1 yard on our little quad circle that we're setting up, that would be realistically equivalent to 57.9 millions of kilometers, as long as we measure accurate. So then part B, use this ratio, this 1 to 57.9, to determine how far the other planets would be and fill in the table with 2 decimal places of accuracy. So how far away would you place Venus? How far away would you place Earth? How far away would you place Mars? Let's go ahead and get an idea of what the answers should feel like so that when we get the answers, we can ask, does it make sense? So Venus is further away from Mercury. So the first thing in terms of you asking, does it make sense? Let's say I got the answer as 0.7. That is trash because it's less than Mercury. Why on a scale that's supposed to be proportional, if the distance to Venus goes up compared to Mercury, why would on the scale would it go down? That's terrible. That would not make sense. Let's say I get an answer of 50. Well, the Mercury distance was 57.9. Let's just call it 60. Let's just round it to a kind of a cleaner number. And then 108.2, well, that's about 120, and I'm using the term about very loosely there. But I'm just trying to say this is about 60, this is about 120, or you could say these are about 50 and about 100. I'm just trying to get them close to a whole number apart in terms of a multiplier. So either way, what I'm trying to say here is these numbers are doubled roughly. The distance to Mercury versus the distance to Venus is about twice as much. 60 versus 120 or 50 versus 100. So I expect the answer over here to be about twice as much, so I expect it to be in the ballpark of 2. 50 is not in the ballpark of 2. It's not even close, so that would say I've done something terribly wrong. So it wouldn't make sense. All right, so we're in part B now. Let's actually do the math. So this is literally a proportion table. You can just do everything that way. So you can imagine yourself drawing your box around these four things. There we go. That's it. So we would go 57.9, not 8. I was looking at an 8, sorry about that, over 108.2 would be equal to 1 over x. And then you can cross multiply. The 57.9 would be multiplied by the x. And then the 1 times the 108.2 is 108.2. You then, to solve that, divide by 57.9. Absolutely no excuses in this course to not know how to solve that equation. Will not survive this course without knowing how to solve that. And then you pull out a calculator. Just this one today. And let me clear my screen since that's getting in the way now. So we got 108.2 divided by 57.9. And we get 1.87 when we round to the nearest second place, 1.87. 1.87. So that would be 1.87 for the distance from the sun to Venus. 1.87 what? 1.87 feet, 1.87 Bob Doles, 1.87 oranges, 1.87 million kilometers? No, you're not building a scale in millions of kilometers. You built it in yards. And that is about 2. It's roughly 2. And again, I'm not saying it's super, super close to 2, but it's pretty close to 2. So it makes sense. Earth. Well, again, this is about 50. This is about 150. So that distance triples. So I'd expect this answer to be in the ballpark of 3. Now, it's going to be less than 3 because 58 is closer to 60 than 50. So 150, it's probably going to be somewhere between 2 and 3, but closer to 3, or at least like halfway to 3. Oh, I'm on annotate again, that's why. Okay, so C. No, not C. Still in part B. And let me just switch that letter over here to V for Venus. And then for Earth, we'll make that a letter E. So we can imagine ourselves drawing our box this way, if you want to use proportion table. So 57.9 over 149.6 equals 1 over, and again, we're calling that E for now. So we got 57.9 over 149.6 equals 1 over E. Cross multiply, you'll get 57.9 E equals 149.6. Divide both sides by the 57.9. You get that E is equal to, rounded to 2 decimal places. Come on, calculator, you're killing me. 149.6 divided by 57.9. And we get, does that answer make sense? No, it doesn't. 0.25. That doesn't make sense. And if you can see, it's really teeny, but when I hit my decimal, it didn't actually register. So I made a calculation error. That's just a tiny little boo-boo, but I knew it was wrong because the answer didn't make sense. If you just blindly trust everything and you're not asking yourselves, you're going to write 0.25 as the answer here, and then you're going to get it wrong. So let's try that one more time. Let's be careful, 149.6. And this is why we do things twice when we're on our own, 0.9. Now 2.58, that answer makes much more sense. What the heck? That didn't make sense. 2.58. I'm actually learning why that happens. So 2.58 yards is how far away Earth would be. And then if you wanted to do Mars, you can see that you're going to end up doing 57.9 over. So just imagine extending the box down to here. The top row just keeps getting used. Now you don't have to. I could draw my box this way if I wanted to, because now I have the Earth number. I could certainly draw this as my box. Let me clear my screen first. I could certainly draw this as my box since I know the Earth value, But I've always suggested that you shouldn't use borrowed information if you don't have to, especially if you're rounding that information, because rounding leads to further errors along the line if you keep doing this over and over and over. So 57.9 over, where are we, 227.9 equals the 1 over, now we're talking about Mars. We used M for Mercury. Let's go R for Mars. So R, the third letter of Mars. Cross multiply, you end up getting 57.9 times the Mars variable equals 227.9. You're going to end up dividing both sides by 57.9. And this is another reason I like to keep using the top row, because we keep doing the exact same algebraic step. And if you pay attention, why did I show it that way as a fraction? If you get used to the repetition, you'll go, oh, okay, well, I take the Jupiter number and divide it by the Mercury number. I take the Uranus number and divide it by the Mercury number. I take the Pluto number and divide it by the Mercury number. It would get you the answers a lot quicker. It would be efficient. All right, so 227.9 divided by 57.9. And we get 3.93, which is further than Earth was, but it's not some extravagant number. 3.94, actually, if we round appropriately. So 3.4 yards. So I'm going to very quickly say the answers to the rest of these. I'm not going to make this a quiz, but I do encourage you to do these on your own. I'm giving you the answers for what reason? It's not a homework. It's not a quiz. I'm giving you the answers so you can try it out as practice, because this is one I love doing group work on, but group work just doesn't work for us. So the asteroid belt ends up being 11.85. Jupiter ends up being 13.44. Saturn ends up being 24.69. Uranus ends up being 49.65. Neptune ends up being 77.80. Pluto ends up being 102.17. If that went too quick, go to YouTube, pause, play, pause, play, pause. And that is really all I want to do with this section, aside from making one extra little statement. So let's take off, let's clear the screen. Clear the screen, there we go. Annotate, drop that. I really wish my Windows button worked. I mean, I really wish I didn't have to hit the Windows button so much. It's kind of tedious. Here we are. All right. So some scales, I would actually say most scales. You know what? I don't want to use most. We'll say some. Some, maybe most scales, units. Some do not. A unitless scale implies that the units of the model are the same as the units of the actual. So when we were just doing the planets, that had units. Inside of that scale, if you wrote everything out meticulously, it's one, let's say 1 inch is 72 feet. So that would have units there. Or for our planet problem, oops, wrong thing, this. We said that it was 1 yard was 57.9 millions of kilometers. Now, and when I did these as proportions, I didn't have to do them that way, as I mentioned but didn't go back to. I could have, this is just the proportion equation. We could have just thrown the actual into that, and we would have gotten the same answer. So when we wanted to do Venus, we could have just replaced this with the 108.2. When I wanted to do Earth, I could have just replaced this with the 149.6. When you want to do Neptune, you can just replace the actual with 4509. So I did this as a proportion table, but you can still do this as this scale equation. You can also do it as the y equals kx setup, but it's not as simple as you might think. So that's why I'm not going to talk about it for this particular problem. So again, some scales have units like the one we just practiced with the planets, because one thing was in yards and the other was in millions of kilometers, but some scales do not. So if I had a model where I said 1 foot is 72 feet. So I take a 72-foot, I don't know, Mack truck, and I scale it down to 1 feet, 1 foot, 1 feet, 1 foot singular. That would be a unitless scale because they both have the exact same units, which means I don't have to say 1 foot is 72 feet. I could also say 1 inch is 72 inches. I could say 1 kilometer is 72 kilometers. I could put any units I want as long as they're a distance unit, and it would be true. Now, yeah, I may have been taking a 72-foot trailer and putting it down to 1 foot, but the conversion factor is still exactly true if you did it in yards or meters or kilometers or inches or centimeters or whatever you like. So when you're scaling from the same units, it's called a unitless scale or unitless model. So that is 3.2.
And that is where we are going to end our day together. So when we come back next time, we will start and complete 3.3. It's another section that's on the shorter side. So we'll also get into 3.4. But for now, you know the assignments that you have on the docket, whether they're due today, in 5 days, or in 7 days. So please make sure that you are working on them at a good pace. A few of you may have received an email from me about your work progress, so make sure that you check that out and understand your obligations to this course. Besides that, I hope this was a good learning session, and we will pick up where we left off next time. Have a good day. Have a good weekend. Take care, everybody. Don't forget that a week from today, we will not be holding a live lecture, so that class won't be on Zoom. It'll just be straight to YouTube, and the links would be in Canvas already. All right. Take care, everybody.